my channel. Our most essential learning competency in this session is determine the relationship between differentiability and continuity of a function. Let us recall first the definition of derivative of a function at a number and of course continuity of a function at a given number. Let's do it. Derivative of a function at a given number. A function f is differentiable at the number c if, this is read as f prime of c is equal to the limit of f of c plus h minus f of c divided by h as h approaches 0 exists. For the definition of continuity of a function at a given number, a function f is continuous at x is equal to c if and only if the following conditions are satisfied. A. F of c is defined. B. Limit of f of x as x approaches c exists. And C. F of c is equal to the limit of f of x as x approaches c. Now, how can we determine if the given function is of course differentiable and at the same time continuous at a given number? Here is a theorem. If a function f is differentiable at c, then f is continuous at c. Take note of that. If the given function is differentiable at x is equal to c, it follows that the function is also continuous at c. Now, if f is discontinuous at x is equal to c, then f is not differentiable at x is equal to c. So, these three statements are conclusion from, of course, this given theorem. Okay. So, if f is discontinuous at x is equal to c, then f is not differentiable at x is equal to c. This one is the contrapositive of this. Number 2, if f is continuous at x is equal to c, it does not mean that f is differentiable at x is equal to c. So that means to say, if a given function is continuous at a given point, it doesn't necessarily mean that it is not differentiable at x is equal to c. So there are times that, of course, the function is differentiable, but it is continuous at a given number. And of course, for number 3, if f is not differentiable at x is equal to c, it does not mean that f is not continuous at x equal to c. That means to say there are times that the given function is not differentiable at a given number, but it is continuous at that number. Okay? Let's have this example. Determine whether the given function is differentiable at the given value of c. 1. F of x is equal to cube root of x at c is equal to 0. This is the graph of the function. Now, for us to determine whether the given function is differentiable at c is equal to 0, of course, we need to use the definition of derivative of a function. This one is the derivative of a function definition. So, we will be getting first this one, f of c plus h. We know that our c here is equal to 0, so therefore this is f of 0 plus h. We will be equating it to the value of the function, which is cube root of x. Remember that this one can be written also as x raised to 1/3. So this one is equal now to cube root of 0 plus h. That is now f of 0 plus h is equal to 0 plus h is of course h. So this one is 0 plus h is cube root of h, or simply h raised to 1/3. Okay. Now, for f of c, so we will be, of course, equating this to the value of the function, cube root of x, and then c here is 0. That's the given. This is now cube root of 0. We know that that is 0. Substituting it in this, of course, definition, So we have here the limit of f of c plus h is of course h raised to 1/3 minus f of c is 0 over h as h approaches 0. So this one is equivalent to f prime of c is equal to the limit of h raised to 1/3 over h as h approaches 0. Simplifying this, we have f prime of c is equal to the limit of, this one is, of course, we can cancel it, and this becomes 1 over h raised to 2/3. Why? Because 1/3 minus 1 is, of course, 2/3. That is h approaches 0. So replacing h by 0, that will be the limit of 1 over 0. H approaches 0. So therefore, this one, f prime of c, is not differentiable at, of course, 0. The given function is not differentiable at c is equal to 0 because the limit here does not exist. Let us determine now whether the given function is continuous at c is equal to 0. Let us do the first condition. We have f of c is equal to, of course, cube root of x. Our c is 0. F of 0 is equal to cube root of 0. So this one is 0. So therefore, this one is defined. So f of c is defined. The next is, let us determine limit of f of x as x approaches, of course, c. Okay, so we have limit of course, cube root of x as x approaches 0. So this one is the limit of cube root of 0 as x approaches 0, and this one is also 0. So meaning these two are equal. Limit of f of x as x approaches c is equal to f of c, since 0 is equal to 0. So meaning the given function is continuous at c is equal to 0. So remember that the function is not differentiable at c equals 0, but it is continuous at c is equal to 0. F of x is equal to the absolute value of x at c equals 0. This one is the graph of the function. Let us verify if it is differentiable. Of course, we know that if this one exists, that is differentiable. So let us evaluate first f of c plus h. Equate it to the value of the function, which is the absolute value of x. And then c here is 0. 0 plus h. This one is 0 plus h. We know that 0 plus h is h. So we have the absolute value of h. This is c plus h. Next, let us determine, of course, f of c. F of c, that is, equate it to the value of the function x. C is 0. And this one is, of course, absolute value of 0 is 0. So this one is f of. Now substituted here, we have f prime of c is equal to the limit of absolute value of h minus 0 divided by h as h approaches 0. Remember that if we have the limit of h, absolute value of h minus 0 over h, as h approaches 1 from the right, I will be using here, of course, 1. It is because 0 has no sign. The absolute value of this is, of course, 0 still. Here, the absolute value of positive 1 is 1. The absolute value of negative 1 is still 1. So this one is equivalent to, this one is absolute value of 1, 1. Same as if we have h minus 0, h approaches 1 from the left. So this one is also equal to 1. Since the function is already differentiable at c is equal to 0, let us now determine whether it is also continuous at c equals 0. F of c is equal to the absolute value of x. So our c here is 0. Absolute value of 0 is, of course, 0. It is defined. Next, the limit of f of x, that is absolute value of x, as x approaches 0. So this one is equivalent to the limit of 0 as x approaches 0. So this one is also 0, and they are equal. So meaning to say, the function is differentiable at c is equal to 0, and at the same time, it is continuous at c is equal to 0. F of x is equal to x squared minus 2x at c is equal to 1. So this is the graph of the function. This one is a parabola that opens upward. So again, this is f of x is equal to x squared minus 2x. c is equal to 1. So let us determine whether the derivative of the function exists. So f prime of c is equal to the limit of f of c plus h minus f of c divided by h as h approaches 0. So let us evaluate first f of c plus h, equate it to the value of the function, and then our c here is of course 1. 1 plus h is equal to, replace all the x's by this, 1 plus h squared minus 2, 1 plus h is equal now to square of binomial 1 plus 2h plus h squared minus 2 minus 2 minus 2h. Okay, so simplifying it, we have f of c plus h now is equal to h squared. This one is 0, and this one is negative 1. So h squared minus 1. Let us evaluate f of c, equate it of course to the value of the function, and then replace c by 1. This is 1 squared minus 2 times 1. We have 1 minus 2. This is equivalent to negative 1. So let us now of course replace this here. F prime of c is equivalent to the limit of h squared minus 1 minus negative 1 divided by h as h approaches 0. So this one is the limit of h squared. This one is negative 1 plus 1 is 0 over h as h approaches 0. So we can cancel it, and then we have the limit of h as h approaches 0. That will be equal to, of course, 0. So meaning to say, it is differentiable at c is equal to 1 because the derivative exists.